we will discuss words, that is hypothesis. Let us see the definition of hypothesis. So they will be proposing an equation or formula and they will be testing it. It may be, they may accept it or they may reject it. So that is hypothesis. And if you come to the postulate, we are assuming and the assumed thing is correct or it is true. Okay, that is what a postulate. Okay, the difference between the hypothesis and this postulate is this. Okay, there is no way, and without any proof, just we are assuming and but we are thinking that it is true. Okay, that is postulate. Here we are having 5 quantum postulates. Okay, we know now what is the theorem, what is hypothesis, and what is postulate. Okay, postulate is one. Is we are assuming something and without any proof, and it is a true. Okay, that is a postulate. Now let us see a few more new words: observables and operators. Okay, so an observable is nothing but just it is a physical quantity, we can measure it. But operator, in quantum state, just we are using the word operator. Okay, operator can be determined by using some operations. Okay, so we are having certain operators and operations. Let us see this. These are observables and operators. So we need only 2 important things: Hamiltonian operator, and that is the thing what we require. Okay, in order to introduce that, so we are going for that. So what is Hamiltonian operator? It is an addition of kinetic energy either in 1-dimensional or in 3-dimensional. That is T plus E. Here we are seeing T and E. Okay, both the things. You see this, these are the 2 things which we are adding. Okay, that is Hamiltonian operator. And other things, even momentum and other things are there, but we may not. Observable and operator. I think you may have understand the difference between these both. What is observable and what is operator. Okay. Now let us see the Planck's equation and few important relations related to Planck's equation. A is equal to h nu. H is a Planck's constant. Nu is a frequency. And not only this C is equal to h nu, even we can write nu is equal to C by lambda, or nu bar is equal to 1 by lambda. Nu is equal to C nu bar. See that we can write this E is equal to h nu in so many ways. How we can? E is equal to hc by lambda, or E is equal to hc nu bar, or E is equal to hc by lambda, or hc nu bar. Okay. This is the Planck's equation, and here lambda is a wavelength and nu bar is a wave number. Okay, and we know well already the de Broglie's equation. Lambda is equal to h by mv. Here onwards we are considering the subatomic particle or small scale object or ultra scale or nanoscale particles will have both the natures, that is the wave nature it has and particle nature it has, as per our de Broglie's hypothesis or de Broglie's equation. Okay, this what he has compiled or he has correlated the Planck's equation with Einstein equation. E is equal to h nu and E is equal to mc square. Then if u equal both, so finally lambda equal to h by mb. We get here. You see one more simple important difference, classical versus quantum. Classical is applicable for visible large objects, and quantum is applicable for invisible or ultra small scale objects. In classical thing, we can see the motion of the bodies and we can observe it physically, just we can see it. But in ultra scale or invisible thing, even if you want to define energy, it is an energy will be having both wave nature as well as particle nature. That is what our assumption. Okay. So now, as I am discussing, we are having 5 quantum postulates. First postulate will tell state of a system. Okay. Just if you know the headings, that's enough. You don't worry about these postulates because it is not in our syllabus. Okay. In order to understand the quantum chemistry or in order to understand the Schrodinger wave equation, just I am introducing these quantum postulates. The first one is state of a system, that is psi, a bracket, and observables and operators. We have seen what is observables and operators. Observable is a physical quantity which can be measured. An operator which can be calculated by a certain operations. Okay. And here measurement of an eigenvalues with the help of eigenfunctions. Okay. And probabilistic output of a measurement, that is in quantum postulate 4, and the evolution of a physical or chemical system here. Okay, these are the 5 quantum postulates. From this, what we are, and quantum postulate 3, h psi equal to E psi. Here only our Schrodinger wave equation will start. And so you can define what this Schrodinger wave equation will. Okay, it describes the energy and position of an electron in three-dimensional or a space with respect to time. You see here 2 factors, one is space and one is at time. Both the things, with respect to these things, we are describing the energy and position of an electron in space. Okay. Schrodinger wave equation considers wave equation, it will consider, and de Broglie's hypothesis it will consider, and conservation of energy, kinetic energy and potential energy it will be. Okay. Now, so as per Schrodinger wave equation types, we are having 2 types of Schrodinger wave equations. If you want to derive the solution, then we can derive the solution in for 2 equations, that is time dependent Schrodinger wave equation and time independent Schrodinger wave equation. Here you see here high h cut or high h bar, a d by dt and bracket of psi of t equal to h psi of t. Okay, psi of t we are writing it in bracket. Okay, so the terms or words or the letters what we are using in this equation, just psi is a wave function, h is an Hamiltonian operator, t is a time, I is an imaginary unit, h is a Planck's constant. Okay, and one more thing, this is a bracket and this indicates an operator. Okay, cap, and this d by dt integrates this d by dt tells us it is a definite differentiation. Okay, it is a definite differentiation. And time dependent Schrodinger wave equation with respect to or with the base of position. Just you see here position, we are taking it in x. Only in 1 dimension we are writing this. If you want to write the time dependent Schrodinger wave equation position for three-dimensional thing, we have to write psi of x, comma y, comma z, comma is another thing we will be. Okay. See. Here we have written one-dimensional thing, that is I h cut or h bar dou by dou t of psi t equal to. Here I will tell you what are this. It will come in one-dimensional equation also. We will discuss what is this. Okay. So now, yesterday also we have introduced the time-independent Schrodinger wave equation. Okay. H psi equal to E psi here. H cap or H is an Hamiltonian operator. Psi is a wave function, is an energy, it is a sum of kinetic energy and potential energy. Okay, where psi is a wave function, which is an Hamiltonian operator, is energy for the system. Okay, and what is this Hamiltonian operator? As we have seen a table in earlier slide. Okay, operator. This is an operator. Hamiltonian operator is a kinetic energy and the potential E plus V. Just that is thing we are writing here in the form of a numerical mathematical representation, that is H cap equal to minus H square by 8 pi square m. Why minus is arising here? Since our Schrodinger wave equation is having I, imaginary unit, I is equal to square root of minus 1. That is the reason we are getting here minus, and dou by dou x square plus dou by dou square by dou y square plus dou square by dou z square. This is an operator. This is also one more operator, that's we are writing it in delta square or Laplace operator. So we will be indicating this thing with nabla. They will be calling it is a reverse triangle. Okay. So instead of this, dou square by dou x square plus dou square by dou y square plus dou square by dou z square will be. So now if you combine this Hamiltonian operator and Schrodinger equation, this H psi equal to E psi, but we have to substitute Hamiltonian operator in this equation. H psi equal to E psi. We are writing its capital H cap. What is that? The value of H cap we are substituting in H psi equal to E psi. Okay. See that the entire equation will become this. This is a Schrodinger equation. Now let us simplify this. This is a three-dimensional Schrodinger wave equation, time independent wave equation. Okay. Time independent wave Schrodinger wave equation. Let us, as I told you, dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. Instead of that, we can write Laplace operator. Okay, that is delta square I used to call. Okay, is an delta square psi. Okay, see this now. If you simplify time independent Schrodinger wave equation, delta square psi plus 8 pi square m by h square into E minus V into psi equal to 0. You see here, instead of this term, we are writing delta square psi. Okay, this is an operator. Dou square by dou x square plus dou square by dou y square, dou square by dou z square. Instead of that, we are writing this delta square, and psi we are writing, and 8 pi square m by h square into E minus V into psi equal to 0. We are bringing E psi, or we are sending V term into that side, or otherwise we are having a negative term at this. You see that what we are having a negative term. This term we are sending it to that side, and we are taking psi as a common term, and we are making it to equal to 0. Okay, we are rearranging, we are simplifying this time independent Schrodinger wave equation. This is a three-dimensional Schrodinger wave equation. Okay, One-dimensional Schrodinger wave equation is this: dou square psi by dou x square plus 8 pi square into m by h square into e minus v into psi equal to 0. This is what the equation you should remember. This is a simple thing. It is not in three-dimensional. Even it is very simple. Just you see, dou square psi by dou x square. Here dou indicates the partial differentiation. Okay. 8 pi square m by h square into e minus v into psi equal to 0. Now let us see. We have to see the solution for this equation in one-dimensional box. Let us assume one-dimensional box which is having x and y. We are not taking a z coordinate here because it is in one-dimensional. We require only x, y, but before going to get the solution for this Schrodinger wave equation in the form of 0-point energy, in the form of quantum numbers, in the form of other things, what we will see the solution for psi first. It's psi equal to E psi. Okay, we see the solution for psi. Let us, before going to solve the solution for this equation, we are assuming three important conditions. What are these important conditions? Psi, wave function isn't continuous. That means we are assuming that if electron is there, it will be this wave function of this electron. We are telling that it is a continuous. Okay. And it is a finite. We cannot tell it is an infinite. That means if it is infinite means the entire universe becomes single electron. Okay, that is against our the solution. Okay, we have to assume that it is a finite. Wave function is a finite and wave function is a continuous. There should not be any break, and the electron will be at one point and there will be break, and you can see electron in somewhere. It is not acceptable. Okay, that is the reason the condition is the wave function condition. It is a continuous and it is a finite, and it has a value at all the points. It has a value at all the points. Go for the solution. Before going to that, just we are assuming that the mass of the electron is m and the electron is moving from x is equal to 0 to x is equal to a. Let us assume the one-dimensional box, okay? And within this box, let us keep our electron in somewhere. Let us what it will be. So now the electron is at this point. Let us assume first, okay, this is a one-dimensional box, and or otherwise let us keep a dot. Instead of writing text, I will make it electron and is with red or green. Yes, red color. I will fill it with red color. What it is an electron. Now electron is inside the box, we are assuming. And one more thing, for psi wave function, we have to discuss here three conditions. Okay, the conditions for wave function. Why? Let us assume, just we'll discuss why we have to assume the three conditions first. Okay, three conditions why we should assume. The first thing is, first condition is wave function is a continuous and wave function is a finite and it has a single value at all points. These are the three conditions. Okay. Why we are assuming these three conditions, I will tell you. Okay. So let us, if you want to prove you are in classroom, we are having a method. We are assuming you are not in the classroom. If you are not in the classroom, we have to see some consequences. And since there is no complaint or there are no any observed consequences, what we are, our assumption is wrong and you are in the classroom. This is what our way, how we prove. This is a contradictory method. In similar way, we are assuming the conditions, okay, wave function, and the wave function has these three characters, and the de Broglie is considering the two natures, one dual nature, that is, one is particle nature and wave nature. Okay, and this is the de Broglie's theory, particle nature as well as wave nature. Okay, so now let us, if you want to derive the solution for wave or wave function or energy, we have to derive the solution for these two parameters, that is energy and wave function. Prior to that, we are assuming the conditions for wave function. What are the conditions for wave function? Then wave function is a finite and wave function is a continuous and wave function has a single value at all points. Let us, so now electron is at this point. Now let us, if it is having a wave nature, electron will be moving, it has a wave nature. Now let us, now electron has a both particle nature and wave nature according to the de Broglie's. Now let us assume this is an electron, it has wave nature. While deriving the solution for wave function, we are considering the wave nature. If you want to derive the solution for energy, or if you want to derive the energy, we will assume this electron as a particle nature. Without consideration of this dual nature, you cannot derive the solution for Schrodinger wave equation. Schrodinger wave equation. Okay, this is the main requirement for, this is the main requirement for this Schrodinger wave equation solution. Okay, let us, this is the mass of the electron. Let us assume m. What is the mass of the electron? Mass of the electron is m, small m. Let us, so now, and inside the box one more condition is it has both potential energy and kinetic energy. Okay, both energies it has. Okay, potential energy V or PE, yes, and kinetic energy Ke. It has a both energies. While, and one more thing, beyond the, or this is the box inside. Okay, that is a one-dimensional box. That is what we are. Let us assume outside this box what happens, the conditions for the outside the box. Let us, Here potential energy is zero or constant inside the box. Okay. The kinetic energy will be there. Okay. It is an outside the box, the potential energy will be infinitive. Okay. Infinitive. Okay. Let us, and one more condition is, we are assuming that this is an wall, that is one dimensional box wall. Let us assume that the x is equal to 0 here, okay, and the length of the box and through the wall, let us assume here it is x is equal to 0 and here it is x is equal to a. That means the length of this thing is a now. Okay. So now, why we are going to solve this energy and wave function? If you solve energy and wave function, we can clarify so many our complications. So whether electron is existed or not, what is the position, what is the orientation, what is the energy, this type of questions can be answered if you derive the solution for this H psi equal to E psi. Okay. So now inside the box potential energy 0 or constant. Okay. 0 or constant. Okay. And potential energy will be there definitely. And outside the box potential energy is infinity. Why we are assuming this one-dimensional box? Let us assume this is an orbital. One-dimensional box is an orbital. What is orbital? Actually, anybody can answer. Yes, what is orbital? Please unmute yourself. And please, what is orbital?
It contains the electrons.
A probability of
finding an electron is the maximum.
Maximum. Let us assume this one-dimensional box is a orbital, s orbital. Let us. That means the probability of finding electron inside this box is maximum. Okay. Outside the box, the probability of finding electron will be 0.
Minimum
and
0.
That means we are having two solutions for this. Now, two things. Inside the box, we are having a one solution. Outside the box, we are having a one solution. You know what is the potential energy? That is P. We will be writing it with capital V, and yes, you see, instead of writing H psi and E psi, what we are writing in one-dimensional box, only one parameter will be here. And here, why we are using dou, I will tell you. This is a partial differentiation. What is the difference between d by dx and dou by dou x? Anybody would be able to? Please, if anybody knows the difference between dou by dou x and d by dx? Yes.
Dou means partial difference, sir. Dy means differentiation.
Yes. So why we are, in which case we are using this partial differentiation? Yes.
In particular area or sun?
No, let us, if you are having more than one variable, let us, if you are varying one variable, automatically other variables will be depending on the one variable, whatever we assuming we are. In such case, we will be using the partial a differential equation. Dou square psi by dou x square plus, okay, this is what the thing. And here 8 pi square m by h square into e minus v into psi. Okay, sorry, this, I'm not getting this. Here this is 8 pi square m and h square capital, yes, let us.
Sir, where you're using that, sir? In which software, sir?
Me, equation editor, yes. You are unable to see it.
No, sir, we can see, sir.
Now you can see, no?
Yes, sir.
Okay, don't consider this Z, it is an, we are going to delete that. Okay, now this is perfect. H psi equal to E psi, that is also Schrodinger wave equation, and dou square psi by dou square psi by dou x square plus 8 pi square m by h square. E minus V, what is E? E is a total energy, V is a potential energy, that means this is a kinetic energy. E minus V is, what is the term of E minus V? It is a total energy, energy is E. If you are subtracting V, that is a potential energy, what is E minus V term? It is a kinetic energy, okay. The entire thing now it will be 0. Okay, this is what the Schrodinger equation, simplification or simplified form of this H psi equal to E psi is what? Dou square psi by dou x square plus 8 pi square m by h square into E minus V into psi equal to 0. Okay, this is what the Schrodinger equation. Let us assume H psi equal to E psi is equal to equation 1 and this is equation 2. Let us assume this is an equation 2. Okay. This is in software sometime, please, if you are having any problem, please let me know. Okay. You could able to see the entire screen. Yes, is it?
Yes, yes, sir. Yes, sir.
No problem, huh? Visibility and all is okay, no? Yes. So now let us, we are having two solutions for this equation 2. What are those two solutions?
Time dependent and time independent.
Outside the box solution and inside the box solution. We are having some chat box there. Okay, let us see the solution outside the box first. What is the solution first? Outside the box. What are the conditions outside the box? See, first condition or first this thing is, we are having a solution for wave function in outside the box. Okay. For outside the box, what are the conditions? A potential energy V equal to infinity. That means this term is E minus V. If you are substituting V equal to infinity at this point, okay, V is equal to infinity. If you are substituting V is equal to infinity in equation 2, what happens? Yes, the entire thing will become what?
Infinity.
Infinitive. That means this term is bigger term, infinitive into psi. Okay, what is the, if you substitute this, V is equal to infinitive in dou square psi by dou x square plus 8 pi square m by h square into E minus V into psi equal to 0. We have to substitute V is equal to infinitive. If you substitute V is equal to infinitive, we get infinitive into psi. Okay, what we get? We get infinitive into psi. Let us see that now. What is the meaning? Infinitive into psi. What is the meaning now? We have to find the solution for psi. Now, if you are keeping infinitive in that place, what happens? Dou square psi by dou x square plus infinitive, and this 8 pi square m by h square into e term, it will become a negligible term. Now the dou square psi by dou x square equal to infinitive into psi. Now what is the condition? And so now, since this one minute, just I'm writing now. When it is infinitive psi equal to 0, when? Please, sorry. Students, please, could you able to? When this infinitive psi will become 0? When psi should be
0.
0 or 1?
0.
Psi should be 0. Now, that means the probability of finding electron outside the box will be
0, sir.
0. Okay, that means we got a solution for outside the box, that is outside the orbital. We proved. Now what is our solution? Outside the box, the probability of finding electron is 0. Okay, for outside the box we got the solution. Okay,
Sir,
yes.
why potential energy infinity outside of the box, sir?
No, just we are assuming three conditions. You let us. We are assuming one electron is there inside the box. It is a finite. It is not infinite. We are assuming three conditions. According to that only, we will be outside infinity. Potential energy of the thing will be infinity. Okay. The condition is, if you are assuming one electron and nature and wave nature, and entire universe will become only single electron, but it is against our assumption. What is our assumption? We are assuming three conditions. Wave function is a finite and wave function is a continuous. If wave function is infinitive, what is the meaning? The entire universe will become single electron. Okay, but it is against our assumption. Either the electron should present inside the box or outside the box, and the potential energy, if it is there inside, it is a 0 or constant. If it is outside, the potential energy will be infinity. And if you substitute these conditions in equation 2, what happens now? Infinitive into psi equal to 0. Okay. So now when this infinitive into psi will be 0, psi should be 0. That means outside the box, the probability of finding electron is 0. Okay. In one-dimensional box, the probability of finding outside the box is 0. Have you understand this concept? Yes, please. If you are having any doubt, please.
Yes, sir.
Yes, is it clear?
No, sir.
And
No, sir, I didn't understand.
it is a finite. Okay, it is not infinite, and it is a continuous. Continuous means wave function should be continuous, and electron we are assuming that particle and wave. let us assume up to certain extent if it is having a waveform, and in some place we are unable to see, and again if you are seeing the wave function, it is a not continuous. That means in middle place electron will be invisible. It is against our assumption. That's what we are assuming, that certain conditions. The quantum theory or quantum chemistry is a probabilistic chemistry. I told you already. That means it is within s orbital where will be your electron. You are telling only the probability of place, probability of finding electron. That means it may present in s orbital, and you cannot define exact position of the electron inside the orbital. Okay, it will be everywhere. We are assuming. That is what the meaning. Okay, wave function is a continuous, wave function is a finite, and it has a value at every, it has a single value at all the points. That is what these are the three conditions. Okay, is it clear now?
Yes, sir.
Yes. 1 minute.
Clear, sir.
In class lo unnaka mali. Sorry, just next inside the box, let us. What is the conditions for inside the box? Yes, please. What are our conditions inside the box? Potential energy is
Zero, sir.
constant. Okay. Now if you keep V term as a 0, what will happen? Yes, inside the box we are going to solve the now V term will become 0. Okay. Now this will become 0. Okay. And now the conditions as per our thing, what conditions we are? V is equal to 0 inside the box. Now if you are keeping, you are getting exact term, that is 8 pi square m by h square into e into psi equal to 0. Now, if you substitute this potential energy is equal to 0, what will be? Dou square psi by dou x square plus 8 pi square m by h square into e into psi equal to 0. This is what we are getting. In order to simplify this equation, we are assuming that this 8 pi square m by h square as a into e as a term called k square. Okay, I will tell you why k square. Okay, I want to convert this equation 3. I want to convert this equation 3 in such a manner. Okay, I want to make it. Now what I will be writing this equation as, okay, I will be assuming that it is a k square value. Okay, what is that? Directly I am writing a k square see that now it was simplified. These look like a simplified form of equation 3 above equation. Okay, have you got the thing? Dou square psi by dou x square plus k square into psi equal to 0. Okay. Now, this is the term what we are k, principal quantum number. K here only we are introducing, but let me explain. After that, we will be knowing the what is this k. Okay. Dou square psi by dou x square plus k square into psi equal to 0. Now, k square is equal to what? What is the k square? The term
8
is,
pi square m by h square.
yes, that we are going to write k square is equal to 8 pi square h square into E. You see that we are getting a relation between energy and principal quantum number. I think you might have already. So now we are getting the solution for what? Energy. We are updating, just let us see that k square is equal to 8 pi square m by h square into E. Okay, this is what one more equation. We are assuming that k square is equal to 8 pi square m by h square into E. If you are substituting in that, so we are getting that simplified equation k square into psi. Now, this type of equation, if it is there, let us give the numbering for this equation. This is equation 2, okay? The first one is equation 2 and 3, 4, 5 and 6. Now let us, for equation 5, we see the solution, okay? For equation 5, let us, this is the equation 5, okay? Now the solution, standard solution for this equation 5 is psi is equal to e power mx. This is what the solution for, as we are having ax square plus bx plus c, we are having a standard solution. Similarly, for the equation 5, we are having a solution. So what is that? Psi equal to e power mx, and this is the solution for equation 5. Let us assume the solution for equation 5 is what? Psi equal to e power mx. This is equation 6. Could you able to catch my points, please? If you are having any difficulties, this is one of the important question in unit 1. Okay, that is derivation of a solution for energy and wave function. Okay, psi is equal to e power mx. Now let us substitute this equation 6 in equation 5. What will be the, let us substitute e power mx and you cannot see since it is a third thing, e power mx. Yes, have you seen equation 7? Would you able to see the equation 7? Yes. Yes, please respond somebody. Yes, equation 7. Could you able to see?
Yes, sir.
Yes, sir.
Yes,
So
sir.
what we have done? We have
We
simplified.
have replaced it as psi equal to e power m.
Yes. Now, please tell me if you are differentiating or if you are doing a partial differentiation of e power x, what you get? What you get? Yes, e power mx, if you are doing what you get? 2 times if you are doing what you get? Differentiation of e power mx. 1 time if you are doing m into e power mx, you will be getting. 2 times if you are doing what you get? M square into e power mx. Okay. What is the solution for this dou square into e power mx? If you are doing the differentiation 2 times, e power mx will become m square into e power mx. And now, if you know the maths, it will be easy. If anybody is having background of mathematics, this biology or life sciences, please. 2 times if you are doing the differentiation, you get m into m. Okay, that is m square. We get directly m square into e power mx. Yes, you see that. Now let us take the e power mx common. Okay, what you have to? Let us take e power mx common and you get this value. That is, yes, this is what you get. E power mx, m square plus k square into e power mx equal to 0. Now, as per our thing inside the box, what is our condition? Psi is not equal to 0 because we are assuming that it is inside. Okay. As per our condition, e power mx cannot be 0. Now, what is the other condition now? Other possibility, m square plus k square
M
is
square plus
equal
K square equal to 0.
to 0. Okay, that is what the condition. Okay. Up to this, are you clear? Yes.
Yes, sir.
Now the condition is m square plus k square equal to 0. Now it is giving us the complex number thing, m square is equal to minus k square. You send that side. And if you want to see the solution for this, yes, what will be the solution? M is equal to plus or minus. Yes, what will this type of ik? We are using some complex. M is equal to plus or minus ik. Okay, this is what. Yes, now the solution for m is equal to plus or minus ik. Now you substitute this m value in equation 6. What you get now? Please, we are assuming that solution for equation 5 is equation 6 and we are substituting, we are assuming and we are substituting the psi value. Okay. Now we have to solve the psi. For the solution, what we are doing the differentiation and we are making it m square plus k square into e power mx, and as per our condition e power mx cannot become 0. Have you? And now if e power mx is not equal to 0, m square plus k square term equal to 0. Now if you want to know the m value, if you are sending the k square that side, and square root of k square minus k square will give us the plus or minus ik. And now we have to substitute this m value in psi is equal to e power mx. And we will substitute. Let us, we need some space for this here itself. What we get, psi power psi is equal to a1. Then let us introduce here new terms. A1 into e power plus ikx and plus a2 into e power minus ikx. Let us, it will be a lengthy thing. Anyway, just wait for display. Just we are getting the updated equation. Yes, now we are substituting this m is equal to plus or minus ik value in psi is equal to e power mx, and we are getting psi is equal to a1 into linear combination of a1 a2. It's like a wave function. This is an amplitude a, okay, it is an constant. Psi is equal to a1 into e power plus ikx plus a2 into e power minus ikx. Okay, this is what you get. So now if you are having any doubts, please let me know. Yes, is it okay up to this point?
Yes, sir.
Inside the box we have, outside the box we are having a solution for the psi. Okay. What we are assuming first? We are assuming the electron, subatomic particle, is present with mass m. Okay. That mass only here 8 pi square m. H is a Planck's constant, phi is a constant, psi is a wave function, E is equal to the kinetic energy plus potential energy sum. Total energy minus potential energy will give us the kinetic energy, okay, into psi equal to 0. Okay, you can write either equation 1 or equation 2, and this is a time independent equation. Okay, time independent equation and Schrodinger one-dimensional equation. But normal, you might have seen already three-dimensional equation, that is dou square psi by dou x square plus dou square psi by dou y square, dou square psi by dou z square plus 8 pi square m into e minus v into psi equal to 0. That is a three-dimensional equation. Okay, but we are interested, and we are, as per our syllabus, and we are stick to this, that is a one-dimensional equation. That's what dou square psi by dou x square plus 8 pi square m by h square into e minus v into psi equal to 0. Okay, are you clear with this? Students, if you are having any doubts, please let me know now itself. We are solving the solution for wave function. We have already solved the solution for energy. Here in assumption itself we have solved k square equal to 8 pi square m by h square. If you want energy, what is the solution? K square h square by 8 pi square m. That is what the solution for energy. And what is the k here? This is the principal quantum number. What is the k? K is what?
Principal quantum number.
Principal quantum number. Let me introduce all the 4 quantum numbers. First we are introducing only one. Let us. We got the solution for energy. Here itself we got the solution. What is the solution for energy now? We are assuming that, yes, you see that we got the solution for energy. E equal to k square h square by 8 pi square m. This is what you might have heard already, n square h square by 8 pi square m. As per Bohr model, you might have already seen this, but you don't know why it is coming, how it is coming. In this, due to this it is coming, okay? Now we are getting the solution for energy. What is the solution for energy? E equal to k square h square by 8 pi square m. And even we are going to find the solution for wave function. That is psi is equal to a1 into e power plus ikx plus a2 into e power minus ikx. These are the solutions for this wave function and as well as energy. Still we have to find an full complete solution for wave function. Let us, it will take 1 more hour, maybe next hour we will be getting the solution for wave function, entire solution for wave function. Now we got the solution for energy, okay? Where we have started from our Schrodinger wave equation, and we are assuming the conditions, and we are considering the both natures, and we are assuming the electron with mass m, which is present in a one-dimensional box, where it is present at x is equal to 0, and outside the box potential energy is infinity, inside the box potential energy is 0. Okay? This box is nothing but it is a orbital. It is a orbital. Yes. Either it is a s orbital or p orbital. You cannot find electron outside the orbital. See that? That's what we are telling numerically with scientific way. Okay. We know that electron cannot present outside the orbital. Okay, we know already. But we are proving, just you see how in mathematics how we are going in contradictory way or contradictory method. Okay, this is the solution and we are going to get the solution for psi also maybe in next class. Let us. Okay, are you clear with this?
Yes, sir.
If you are having any doubts, please let me know. Okay.